In this video, we will look at the semantics of SL. Um, so these are going to be given in terms of truth tables. And so truth tables are important because they do two things. One is they provide a semantics, right? They give the meaning for the connectives of SL, and they allow you to interpret sentences of SL. But another thing is that they give a mechanical procedure for evaluating whether sentences of SL are true. And that then provides this. It means that SL is decidable. So you may remember these concepts from earlier on, right? Logical truth, falsity, and indeterminacy, consistency, equivalence, validity, entailment. Because of truth tables and then a couple of other procedures, um, we have algorithms for determining whether these properties hold for SL, which is this is a really valuable property to have for SL. You know, most logical systems you don't have this, so this is really really good. Um, Before we start getting into truth tables, though, what we'll actually do is we're going to go back to the definition of sentence of SL. Because what we'll do is we're going to look at this again and use it to introduce some definitions that we're going to need for talking about truth tables. So if you remember this, this is a recursive definition, right? So it gives a procedure for constructing sentences of SL. So you have your base step, right? Any sentence letter is a sentence of SL. Then you have your recursive step. So if you take a sentence letter and then you add a tilde in front, you get a sentence of SL. And then if you take two sentence letters, you add any one of these connectives in between them and put parentheses around them. And then remember, we have the informal convention that you drop the outermost parentheses. You get a sentence of SL. Nothing else is a sentence of SL. Okay, so with that in mind, we can start defining some important concepts. First of all, we'll have a distinction between atomic and compound sentences. So any sentence of SL, or sorry, sentence letter of SL is an atomic sentence. Anything else, right? So anything that contains connectives is called a compound sentence. Next, we have the concept of a main connective. So if P is an atomic sentence, so a sentence letter, it doesn't have a main connective. It doesn't have connectives, so it can't have a main one. Otherwise, the main connective is the last connective that you would have added when you were building up the sentence through steps 2 to 6 of the definition. So, for example, if you look at this sentence here, A or B, if and only if C and D. Right. When you were building this sentence up using that definition, you would have had this here, A or B, and this, C and D. And then the last step that you would have had would be to put this triple bar between them and then put parentheses around it that we would have then taken off by informal convention. That's the last step that you would have had, but so that then this is your main connective. With this sentence here, this particular sentence is something it's referred to as Peirce's law. You would have had well, you would have started with A and B, then you would have made if A then B, then you would have had if A then B then A, and then the last step is you would have taken this and had this thing implies A. That's the last connective that you would have added in, so this is your main connective. The components of a sentence are, so to start with, if you have a sentence P, it counts as a component of itself. And then the components are all the parts of that sentence that are themselves sentences of SL. So if you take this sentence here, right, these are all its components. So you have itself, and then everything else that is a part of that sentence that is a sentence of SL. These are not these are parts of the sentence, but they're not components because none of these are sentences of SL, right? Parenthesis C, this string of symbols here, right? They're not sentences of SL, so they don't count as components. Um, the atomic components of a sentence are the parts that are atomic sentences. And then the immediate components of a sentence are the components that are joined by the main connective. So in this case, right, remember that this is the main connective. So these are the immediate components. In this case here, if you look at this, right, not A and C, if you were building this up according to that definition, you would have A and C, and then your last step would have been you would have put parentheses around that and put the tilde in front. So this is your main connective, and then you have one immediate component, which is this. So now that we've got all those definitions in mind, we'll start talking about the semantics of SL. So these are given in terms of truth value assignments. So what a truth value assignment does is it gives a truth value, which is T or F, right, true or false, to each of the atomic sentences of SL. And there are infinitely many of these. So it's assigning truth values to all of the infinitely many of them. So of course, obviously, you can't write out an entire truth value assignment. Um, you can think of a truth value assignment as being a complete description of a logically possible world. This is one way that you can think of what's going on with this, with assigning values to all of these infinitely many atomic sentences of SL. This is how they're thought of actually in modal logic, for example. Now, a truth table, what a truth table for a sentence or a set of sentences does is it gives all the possible truth values that those sentences can have given any truth value assignment. Truth value assignments are infinitely large, but the truth value of a sentence will depend only on the truth values of its atomic components. So it'll depend only on the truth values of the sentence letters that are components of that sentence. Which means then that for compound sentence, the truth table only has to give the truth values that that sentence will have for every possible combination of truth values of its atomic components. So they're not infinitely large. You only have to consider the values that the atomic sentences that are components of that sentence, the values that those could have. But you have to look at all possible combinations of them. So we will now look at an example of a truth table. We're going to build a truth table for this sentence right here. A and B implies A or B. All right. So first step is find all the atomic components of the sentence and list them on the left side of the table in alphabetical order. There are two here. There's A and B, and we put them on the left side in alphabetical order. The order here is important. It's important to have a standardized format for these things. It makes the tables readable. Then what you do is you list all the possible combinations of truth values of atomic sentences on the left side. And the convention by which we do this is you go with the rightmost of all your sentence letters, and then you alternate T, F, T, F all the way down. The next one is going to alternate two T's, then two F's, then two T's, then two F's. And then at this point, we're out, right? We've hit all the possible combinations. If you have more sentence letters, then the next one is going to go, you're going to double the number of T's. So the next one over would be four T's followed by four F's and so on and so forth. This is the formula that you're following in each case. Again, you go by this strict, right, regularized procedure. It ensures that your table is going to be readable and it'll be easy for people to read, easy for people to interpret. It also, if you follow this procedure, it ensures that you are actually hitting all of the combinations. Um, this is actually extremely common when students are building truth tables and they don't follow this order, they end up missing one of the possible combinations. And then your table doesn't work because you don't have all the possible combinations of truth values of atomic sentences. So step 3 is you copy the values of each atomic sentence under their occurrences on the right side. This is standard for algorithmically generated tables. When people are doing tables by hand, actually, this step is very, very often skipped. because that's a lot of writing, and you can kind of just look at the tape, the values over here, and copy them over. It's a little bit easier though, particularly for early on. So at this stage, when you're first starting, I would recommend that you do this. Um, okay. So four, using the characteristic truth tables for the connectives, you determine the values of the compound sentences. So we'll start here with A and B. So what you do is you would look at the characteristic truth table for the connective, and you would look at the values for each pair of values. You would figure out, so what is the value that connective would have given that pair of inputs. So this is an and, right? So what value would an and sentence have given that pair of values, for those two immediate components? So here, you've got both of the components here are true on this line. So if A and B are both true, then A and B is going to be true. And in each of the other three cases, at least one of them is false. And if you look at the characteristic truth table for and I haven't actually copied it out on the slide because it looks exactly like this. Um, every one of them, if you look at the characteristic truth table, though, in each case where at least one of the sentences is false, then the and sentence is false. So it's going to be false in all of these cases. So this is the result that you're going to have. We do the or sentence next, right? Whenever one of the sentences in an or sentence is true, then the resulting sentence, the or sentence is true. So whenever A or B is true, A or B is going to be true. So in any of the cases where one of them is true, it's going to pick up true, and only when they're both false is it going to be false. The next one that we're going to need to do is this horseshoe in the middle. And this one's going to be harder because in this case, first of all, the values were just arranged in exactly the same ways in the characteristic truth tables. Second of all, the values that we were looking at, the columns that we were looking at, were right next to where we were going to be putting the values. Here, the values, so the main connectives of the immediate components that pertain to this are here and here. So we're looking at these two columns. And of course, they're not arranged in exactly the way that the characteristic truth table is going to be arranged. So we're going to have to look at the characteristic truth table um, for the horseshoe and look at what values it's going to have for each of these combinations. So here we're looking at this and this. So it's true and true, true and true. It's going to be true here. Here, false and true. So we're looking at this line right here. It's going to be true. Here we have false and true. We're looking at that line again. It's going to be true. And here we have false and false. So we're looking at this line right here. It's going to be true again. So the result is these are the values that we're going to be putting in. It's going to be all T's. Now, the last step is we mark the main connective with an arrow. And the reason for doing this is it tells you which column gives the truth values of the entire sentence. There are other ways of doing this. People sometimes highlight this or put it in a box. The textbook method, the way that they do it is with an arrow. The important thing is that you're marking in some way or another the way in which which column tells you the truth value for the entire sentence. Now, now that we've completed the table, you can actually look at this and what does this tell us? So what we have here, the column under the main connective is all T's. And what that tells us is this sentence has to be true, right? On every possible combination of truth values, meaning then on every truth value assignment, this sentence is going to turn out to be true. So this is a logical truth. This is something that cannot fail. There's no possible combination of truth values where this turns out to be false. So what you're looking at here is actually a logical truth. If A and B is true, then A or B is true. Okay. If you're making a truth table for multiple sentences, it's exactly the same procedure. The only difference is the way that you format the table. You want to make sure that you put some space between each of the sentences, just so it's clear which one is which. And you need to mark the main connective of each one with an arrow, or by highlighting the column or boxing it in or something like that. So here's an example. This is a truth table with 4 sentences in it, and there's a bit of space between each one, so you can kind of see which one is which, and the main connective of each one has been marked with an arrow. Okay, at this point, what you should do is you should build a few truth tables yourself. In this course, we don't have a really big focus on building truth tables by hand because it's a fairly simple algorithm and it's really boring. The thing is, though, is that the procedure of going through and building the truth tables yourself, the main thing is that it helps you learn how to identify main connectives and being able to pick out the main connectives of sentences and also the main connectives of the components of sentences, right? Like not just the main connective of a sentence, but the main connectives of like the immediate components of a sentence. This is something you need to be able to do when you read truth tables, and it's also something that is going to be really important for when you're doing natural deduction. And building truth tables is a really good way to learn, to get an intuitive sense of where the main connectives of sentences are. So you should definitely practice by building a few of them yourself. Before we move on to what's going to be our focus, which is learning how to interpret what the um, what the truth tables are telling you.